Hey everyone, and welcome to today's explainer. Today, we're going to completely demystify a tiny component that essentially acts as an invincible shield for our modern electronics. I'm talking about the Zener diode. We're going to dive into the physics of how it actually works, why it totally defies the rules of standard components, and how it so brilliantly regulates power. Let's just jump right in. Now, think about this for a second. Have you ever actually stopped to wonder how we protect our highly sensitive electronics from sudden, catastrophic voltage spikes? I mean, we plug these incredibly complex music systems, high-end amplifiers, and delicate oscillators right into the wall, and we just totally trust that a random surge of power won't completely fry the internal circuitry. How is that even possible? Well, the secret actually lies in a very minute, almost microscopic structural difference within one specific type of semiconductor. So here's our game plan for today. We'll start by comparing Zener to normal diodes, then look closely at the heavy doping effect. We'll define exactly what Zener breakdown is, contrast it with avalanche breakdown, see how temperature completely shifts the dynamic, and finally look at some real-world applications. All right, Section 1, Zener versus normal diodes and the reverse bias rule. So in a standard forward bias setup, a Zener behaves exactly like a normal diode. But, that's not actually why we use it. The true magic, the absolute core of what makes this little component so special, emerges entirely in the reverse bias condition. Just as a quick refresher, reverse bias simply means the p-type of the p-n junction is connected to the negative terminal of your external battery, and the n-type is hooked up to the positive terminal. It's in this specific environment that the Zener diode really reveals its hidden superpower. Moving right along to Section 2, the heavy doping effect. This is where micro changes give us macro results. You see, the primary physical difference in a Zener diode all comes down to intentional impurities that are introduced during manufacturing. It's honestly a fascinating physical domino effect. First off, heavy doping is applied to both the p-type and n-type materials. Then, step 2, because of this extreme crowding, the depletion layer, that neutral zone right in the middle, becomes remarkably thin. Step 3, a thinner depletion layer naturally causes the potential barrier to drop, which absolutely plummets the resistance against the outer electric field. And finally, because that resistance is now so incredibly low, the diode can conduct electricity at a much, much lower reverse voltage. To put that into perspective, the numerical contrast here is just stark. A normal diode takes a lot of effort to break that resistance. You might need a threshold voltage around 8 volts just to force current to flow backward through it. But the Zener diode? It's an entirely different beast. Because of that heavy doping and razor-thin depletion layer, it can effortlessly conduct electricity backward at just 2 to 3 volts. Which brings us to Section 3, defining Zener breakdown voltage, or the critical point. This is the exact moment the physics completely shift, opening the door to its most incredible capabilities. Okay, so Zener breakdown voltage, or VZ for short, is the specific minimum reverse voltage required to break that thin depletion region and spawn free electron-hole pairs. Even though the barrier is super thin, you still need a minimum threshold of energy to get things going. The literal second you hit VZ, the electrons and holes in the depletion region absorb that energy, they break free, and suddenly, bam, you have a massive rush of free electron-hole pairs immediately ready to conduct electricity. But here's the kicker. The really crucial point is what happens immediately after. Once you cross VZ, you don't just get some chaotic surge. No, you get a controlled, completely stable flow of reverse current. The diode starts conducting backward, but the voltage across the diode remains incredibly steady. It basically locks that voltage into place, even if the external current is fiercely fluctuating. All right, Section 4, Zener versus avalanche breakdown, a tale of two curves. In semiconductor physics, there are really two main ways a diode breaks down in reverse bias. With a Zener breakdown, that ultra-thin layer creates a massively strong electric field, tearing electrons free with barely any effort at all. This results in a very sharp, sudden drop on the voltage-current curve at a remarkably low voltage. Avalanche breakdown, on the other hand, happens in normal, lightly doped diodes. The depletion region there is thick, the electric field is relatively weak, so it requires a much higher breakdown voltage, like that 8 volts we mentioned earlier. The curve for an avalanche breakdown is a lot slower. It's distinctly less sharp than the clean, sudden plunge you see with a Zener breakdown. Let's look at Section 5, the impact of temperature, because, well, heat changes everything. You really can't design reliable circuits without considering the environment, and heat completely rewrites the rules for these breakdowns. So when you increase the temperature around a Zener diode, its breakdown voltage actually goes down. Why? Well, heat is literally providing thermal energy. The temperature itself is doing half the work for you. It frees up electrons in that already thin depletion layer, meaning you need even less external voltage from your battery to trigger the breakdown. It becomes hyper-efficient. Conversely, in an avalanche breakdown scenario, increasing the temperature actually increases the breakdown voltage. You have to push even harder, with more voltage, just to force the current to flow. This incredibly consistent, low-voltage performance under heat is exactly why Zener diodes are so prized for precision control. Finally, Section 6, Real-World Applications. Let's bring it all home. What does all this microscopic physics actually do for us in our daily lives? Think of a Zener diode basically like a heavy-duty voltage regulator for your house. If the power company accidentally sends a massive surge of electricity down the lines, a home voltage regulator absorbs that chaotic energy and ensures only a smooth, safe 120 or 240 volts actually reaches your TV or refrigerator. The Zener diode is doing the exact same thing, just on a micro level. If the input voltage suddenly spikes, the Zener safely conducts that excess current backward right to the ground, all while rigidly maintaining a perfectly stable, safe voltage across your delicate internal circuit. It really is the ultimate electronic bodyguard. Now, because it's such a unique and absolutely vital component, you definitely need to know how to spot it on a schematic. A normal diode just has a straight vertical line against the triangle. But for a Zener diode, you want to look for the distinct Z shape on that line. Those two little bent arms clearly dictate to anyone reading the plans that this isn't just some simple one-way valve, it is a precise voltage regulator. So, we've seen how heavy doping creates that razor-thin depletion layer, allowing a controlled reverse current that acts as a steadfast voltage regulator. But, a Zener diode rarely works entirely alone in the real world, so I want to leave you with a quick question to test your engineering intuition. What other components might you pair with a Zener diode to build a complete, robust protection circuit? Think about current limiting, and think about where that excess energy needs to safely go. Drop your circuit ideas down in the comments. I genuinely read them all to make these explainers even better for you. Stay curious, and I'll catch you in the next explainer.